Okay, yeah, I mean, it's probably like a minute early, but we do have everybody on the roster, so unless there's any great objection, we can go ahead and get started. Um, this is CPE 133, Intro to Digital Design. My name is Gary Perks. I do go by my first name. I do prefer to be called Gary, but I do realize some students feel funny about calling their instructor by their first name. So if you don't want to call me Gary, Mr. Perks or Professor Perks, that's fine. I also respond to hey you as long as it's in my general direction. Okay, so any of those will work. All right, so this is our agenda for today. And in a very short amount of time here, I'm going to jump right into our first lecture. And then after the lecture, I have an activity for you to do that's on the material that I just covered in lecture. So every table should have these, and there should be enough for each person at the table. If there's not, let me know, because I got extra. So if I miscounted, just let me know and I'll get you your own sheets. And then after that activity, I'll just spend a brief amount of time on what's on Canvas. In fact, I sent an email to everyone about a week ago. Did you get my email? Everybody got my email? So hopefully you've had a chance to look at what's on Canvas, but I'll kind of hit what I think are the highlights and also answer any questions you might have about the syllabus or how Canvas is set up. And then I'll talk about the first lab assignment, which is lab 0 part 1, and also give you like a general introduction to the lab after the activity. So if you looked on Canvas, you might have noticed that the classroom protocol is basically, this is a 3-hour class, but I'm not going to lecture for 3 hours. Okay? I know you don't want to listen to me for 3 hours, and I don't want to listen to myself for 3 hours. So typically, there's some variation here depending on the topic of the day, but typically the lecture is about an hour. And then the second hour is to do an activity, which is a group activity. Okay, again, there'll be an activity on what I just went over in lecture. So that's practice of what I just talked about. And then the last hour is the lab portion of the class, where we work on the lab. So, first hour is gaining knowledge, hopefully. Second hour is practicing what hopefully you just learned during the lecture. And then the last hour is applying what you learned in the first 2 hours. Okay. And the only homework is to finish any lab work that you weren't able to finish during class time. Okay. All right. So, we'll talk more about, what's up there, but I do want to start right into the lecture today, where we're going to talk about number bases and base conversion. Oh, also, I usually start writing on this end of the whiteboard and I work my way to the right. So if you're over in that table, especially because of this post here, I don't know, is anyone from Boston? Anyone go to Fenway Park at any time? I'm from Boston, so I've been to Fenway Park a lot. Fenway Park has that. They have like books right in front of your seat. But anyway, if you're in any seat where you're having a hard time seeing what I'm writing, you're free to move. Okay, you're not anchored to your table. So if you want to move over here, like sometimes people will sit right at like the end of the table, or you just want to bring your chair over and put your laptop on your lap, take notes. You're free to do so. Okay, so you can move around wherever you want. Okay. So what did I just write on the board? Yeah, 1, 2, 3. Very good. Too smart for me. What's that? Well, what I was hoping. Well, can you tell me what I was hoping somebody would say? Yes. Yeah, I was hoping well, what would your parents most likely say? Assuming they're not like a computer engineer, what would your parents or someone who's not an engineer or doesn't know numbers very well, what do you think they would say? I wrote on the board here. 123, right? Because when you see the numbers like this, right, the average person, let's say, would assume it's base 10 because that's what we've been programmed from an early age to view these characters as, right? These numbers as base 10. Because, a long time ago, And you probably don't remember when, but it's in your subconscious that a long time ago, you learn that even though if it's not explicitly shown, there's a point right here. And what do we call that point? The decimal point, right? And just to the left of that decimal point, this is the ones column, right? Then comes the tens column, then comes the hundreds column. Right, and then to the right of the decimal point, you have the tenths, right, hundreds, and so on. Right, but I mean, you learned that so long ago, you don't even think about it now, right? Because it's ingrained in your brain. How many characters do we have in base 10? Like how many numbers are there in base 10? 10, right? 0 through 9. So the number of characters in base 10 equals 10, 0 through 9. And then, you know, a little after you first learned about numbers and what these columns were worth, you know, a little later on, you learned about powers, right? That if you have some number to the 0th power, that's 1, right? And, you know, some number to the first power, some number to the second power, and so on. So a little later on, you learn that this ones column, that's the 10 to the 0 column, right? Because any number to the 0th power is 1, like you learned. You know, this is 10 to the 1, 10 to the 2, and so on, right? 10 to the 3, and we could keep going. This is 10 to the -1, 10 to the -2, 10 to the -3, and so on. Okay, well, the reason I start with what you already know is because for every base, this is true. The number of characters for a base equals the base. And also for every base, you have columns that have certain value, and it's always that base to a power, like the 0th power, the first power, second power, and so on. Okay, so for example, just want to make sure I started it at 4. Yeah, okay, good. For example, a very popular base in digital is base 2. Okay, which is called binary. So how many characters in base 2? 2, right? But again, the number of characters in a base equals the base. And what do you think those 2 characters are? 0 and 1. 0 and 1, right? Because every base has 0 as a character, because in every base you'd have to have something that represents you don't have something. Okay, so the characters in base 2, 0 and 1. And then in base 2, we also have a point. Okay, just like we have a point in base 10. But in every other base other than base 10, you don't call this decimal point, right? Because decimal means base 10. In every other base other than base 10, this point is called the radix point. Radix is just another word for base. Okay? But the radix point, it's the same idea that to the left, you have whole values. To the right, you have fractional values. But what's different when you have base 2 is the base. So right to the left of the radix point in base 2, you have 2 to the 0. Then you have 2 to the 1. Then you have 2 to the 2, 2 to the 3, 2 to the 4, and so on. Right? So this would be the 1s column. This would be the 2s column. This would be the 4s column. This would be the 8s column. This would be the 16s column. Then over here, you'd have 2 to the -1, 2 to the -2, 2 to the -3, and so on. So this would be the halves column. This would be the quarters column. This would be the 8ths column. Okay, so in base 10, as you go column to column, there's a factor of 10. In base 2, as you go bit by bit, because we call each character, you would call these bits. Well, in base 2, as you go bit to bit, it's a factor of 2. Okay, does that make sense? Okay, another base that's used not as much as binary, but sometimes in the digital world is octal. Do you know what base octal is? Can you guess from octo, like octopus? 8. Yeah, this is base 8. So how many characters in base 8? 8. And what would those characters be? 7. Do I have any Jeopardy fans? Does anyone watch Jeopardy? Young people don't watch Jeopardy. All my sections, I think there was like just 1 or 2 people. Okay. Not popular yet. How many people know what Jeopardy is? Like Jeopardy, you just don't watch it, right? You know it, but you just don't watch it. Okay. Well, sometimes in Jeopardy, you know, when you watch the TV show, sometimes they have a category, stupid answers to stupid questions. And it's because the answer is in the question. So you see how many characters in base 8 could be under that category, right? Because there's 8. The answer is right there in the question. I guess you would have to say, what is 8, right, when you answer Jeopardy, but. Okay, but same idea here that in base 8, you'd have a radix point. Right to the left is 8 to the 0, how many 1s? Then you have 8 to the 1, how many 8s? And you have 8 to the 2, how many 64s? And so on, right? You have 8 cubed, which is 64 times 8, whatever that is. And then to the right, we have 8 to the minus 1, how many 8s? 8 to the minus 2, how many 64ths? And so on. Okay, but so you see how it's the same idea as what you learned way back with base 10, right? The only thing that's different is the base. Okay, now another very popular base in digital is base 16. Does anyone know what base 16 is called? Yeah. Right. Hexadecimal. Yeah. Hexadecimal. Or sometimes people will just say hex. So base 16, how many characters? 16. And does anyone know how we get the 16 characters? 0 through 9. Exactly. We go 0 through 9 for the first 10, right? Just like we do in base 10, but now we need another 6 characters, and that's when we start using letters. Okay, so 0 through 9, that's the first 10, and then A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Okay, and then, you know, there's a radix point in base 16, just like the other bases. This would be the 16 to the 0 column. So how many 1s? Then you would have 16 to the 1. Basically. Which is how many 16s? Then you have 16 to the second power, which is how many 256s? And then there's 16 to the third power. Does anyone know what 16 to the third power is? 16 cubed, or 16 times 256. Do you have a calculator? I know what it is, but I just want you to figure it out. So what is it? 16 to the third power. 4,096. Yeah, this would be the 4,096 column. And then there's 16 to the fourth, that's 65,536, if I remember right. And then over here, you know, 16 to the minus 1 is how many 16ths? 16 to the minus 2 is how many 1 over 256s? Okay, and you could keep going. Okay, but again, what you learned about base 10 a long, long time ago, conceptually, it applies to all bases. Now, in the digital world, and in this class, and also any digital class you would take, the most important bases, in addition to base 10, right? Base 10 is always important, but in particular, base 2 and base 16 are very important. Okay, for any digital class you take. Octal, not so much. I mean, sometimes it comes up, but base 2 and base 16, those are the two, in addition to base 10, that you really need to be focused on for this class and also any other digital class you would take. Okay? All right, so before I move on to base conversion, does anyone have any questions about what we've done thus far? Everyone okay with it? You see the connection back to base 10? It's probably the most important thing. Okay, so let's go ahead now and let's do some base conversion. And the first base conversion we're going to do is base 2 to base 10. All right, so give me a base 2 number. Give me some ones and zeros. Anyone?
1 0 0 1.
1 0 1 1. Okay, let's have some more bits. What do you want next?
0 1 1 0.
0 0 1 1 0. Is that what you said? Okay, that's good. And then we'll put a radix point, and we'll put 1 0 1. Now, to explicitly identify this as a base 2 number, we're going to put this little subscript 2. Because this could be a base 10 number, right? So, if you want to explicitly, definitely show that it's base 2, just put a little subscript 2. Okay. So we want to take this base 2 number and convert it to base 10. Well, this is where knowing the values of the bits, right? Knowing the value of the columns comes into play. Because again, here's our radix point. So this is the 2 to the 0 bit, which is how many 1s? This is 2 to the 1, how many 2s? 2 to the 2, how many 4s? And how many 8s? And how many 16s? And how many 32s? And how many 64s? And how many 128s? And then how many 256s? This is how many halves, right? Because that's the 2 to the minus 1. How many quarters? 2 to the minus 2. How many 8s? 2 to the minus 2. Okay? And now, wherever there's a 1, okay, wherever there's a bit equal to 1, we have that value. Wherever there's a 0, we don't have that value. Okay, so we just add up the bits that are equal to 1, what the value is for that 1 bit. Okay, so that means we're going to take 256 and add it to 64, add it to 32, add it to 4, add it to 2, add it to a half, add it to an 8. Okay, see, I'm only taking the 1-bit values, right? Because a 0 means I don't have that value, right? 1 means I have that value. Okay, and now we just got to add these up. Now, keep an eye on what I do here, because sometimes I make mistakes. I don't make mistakes on purpose, but sometimes I will make mistakes. So if you see that I make a mistake, don't be quiet about it, just yell it out. Hey, I don't think you're right, or whatever it is. Okay, don't throw anything at me, but just say, hey, that's not right. Okay. All right, so 256 and 64. Let's see, what is that? That's going to be, is that 320? I think that's 320. And then we add 320 to 32 would be what? 352. And then this would be 356, and then 358, and then 5 eighths, right? So it'd be 358 and 5 eighths, which you could write as 358.625. Makes sense, right? Did I do that right? Everybody agree? Okay, so the key thing is, again, you're just taking the values that correspond to a 1, right? You don't take the values that correspond to a 0 bit. Okay, so does anyone want me to do another example like this, or is everybody good? Right, because if you got a different string of bits, it's the same concept. It's just, if the 1s are in a different place, you're adding different values, right? That's the only difference. Okay, so everybody good? All right, let's go the other direction. Let's go from base 10 to base 2. Okay, so we're going to go from base 10 to base 2. So somebody give me a base 10 number and give a number that's in like the tens of thousands. Yeah, something like that. Just any number that's, like between 10,000 and 100,000, something like that. So what number do you want to see? Convert it to base 2. It's your choice.
26,532.
Okay, 26,532, that's what you said? All right, that's base 10, we want to go to base 2. All right, so I'm gonna show you how I would convert this to base 2, and it's based on, what we talked about here. This isn't the only way to go from base 10 to base 2. In fact, if you had a class like this at a previous place, previous school, you might have learned like, a different algorithm. I mean, there's different ways to go from base 10 to base 2, but I'm going to show you how I would do it. And again, it's based on what we talked about here, where, the bits have certain value. So what I would do is I would just start writing out my bit values, starting with 2 to the 0, right? 1. And then we have 2 to the 1, 2s, and 4s, and then 8s, and 16s, and then 32s, and then 64s, and then 128s, and then 2 56s, and then 5 12s, and then 1,024s. And that's space here. Then what? We'd have 2,048s. And then we'd have 4,096. And then we'd have 8,192s. And then we'd have 16,000. See, what's 192 double? That would be what? 384, is that right? If I multiply 8192 by 2, I get 16,000 and then 400 minus 16, right? Is that right? Okay, and then when I double 16,384, I'm going to get 32,000 something, and 32,000 is greater than the number I'm converting, right? So I don't even really have to know what this is, because I know it's going to be a 0, because there's no 32,000 whatever in 26,532. Right, so you see, you write out the value of the bits until you get to a bit that's more than what the number is that you're converting. Does that make sense? Okay, so now I look here and I go, okay, do I have a 16,384 and 26,532? And yes, I do. Right, so that would be a 1. So then I take my number that I'm converting, right, to 26,532, and I subtract this value, the 16,384. All right, and that's going to be what? That's going to be 10,148. Okay, did I do that right? I think it's 148, because 16 would get us to 400, and then 116 plus 32, 148. Okay. Okay, and now I look at the next column here, the next value, 8192. There is an 8192 at 10,148. So that would be a 1. And now I subtract the 8,192. All right, so what is this going to be? This is going to be 1,952. Is that right? Because 1,000 would get us to 9,192. And then 808. 9 plus, yeah, I think that's right. 1,906. Oh, did I? Oh, you're right, right? Because the 82. Thank you. See, I told you I make mistakes, so watch out what I do here. Yeah, that's a 6. But now it's right, correct? I don't know your name yet, but what's your name? Michael. Michael. So now it's right. Okay, thank you. All right, so now we've got 1,956, and we look, well, there's no 4,096s in 1,956. So you see that bit would be a 0. Also, there's no 2,048s, 1,956, right? So that would be a 0. Okay, there is 1,024 in 1956, right? So I would subtract that and make this a 1. Okay, and this would be what? 832? No, 932. 9. Okay, there is a 512 in 5 or 932, so 512. That's going to get us to 420. There is a 256 in 420, so that would be, let's see, what's left over, 164. There's a 128 and 164, so subtract 128. Minus. Let's see, what does that leave? That leaves 36. 6. There's no 64 in 36, so that would be 0. There is a 32 in 36. So that would be a 1, and then we're just left with 4. So all these would be 0, but then the 4 would be a 1, and the 2 and the 1 would be a 0. Right, so you see, just keep going like this until you get to 0. So 26,532 in base 10 is equal to 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 0 in binary. Okay. Now, there's an algorithm that some people use where they take the base 10 number and then they just keep dividing by 2, successfully divide it by 2. And if there's a remainder, that means the bit is a 1. But if there's no remainder, that means the bit is a 0. Okay, that's an algorithm some people use. I mean, if you've used that and that's what you're used to and that's what you like, I mean, you're more than welcome to use that method. I'm just showing you a method that I like to do just because it's based on what we had talked about earlier. Okay? All right, so any questions about going from base 10 to base 2? Everybody's good? All right, let's do next. Let's do. Let's see, which one do we want to do next? We'll do 2 to 60, base 2 to base 16. Okay, so let's see, is that what I want to do next? Have we done base 16 to 10 yet? We haven't done 16 to 10 yet. Let's do that. I'm sorry, I'm jumping ahead. I don't want to do this. Let's do base 16 to base 2. All right, so somebody give me a base 16 number that has 4 hex characters. It makes some of them letters. So what base 16 4 character number do you want to see converted to base 10? Do you have a favorite letter? You want to do your initials? As long as your initial has letters A through F. So what do you want to see? 4 hex characters. Be any 4 that you want. Don't make 1 0 though. A couple letters and a couple of non-zero non-letters. The questions get harder as the course goes on. Throwing you a softball. What number do you want to see? Computer's talking to us. Computer's trying to tell us. What do you want to see? I'm only gonna do what you tell me, so we can stay here till 5 o'clock if you want. Okay, that got somebody going. All right. Okay, F. Then what? F-A-D. Okay, all letters. Fade. Are you fading? Late fade. All right, and then let's add a radix point. We'll put like .4 here. So this is base 16. All right, well, it's the same idea as what we've been doing. You look at what each of the columns is worth, right? So this is 16 to the 0, how many 1s? This is 16 to the 1, how many 16s? 16 to the 2, how many 256s? 16 to the 3, how many 4,090s? And then this would be 16 to the -1, so how many 16s? Okay, so it doesn't matter what order you do this in, but we'll start here. What is F in hex? What number is F? 15. So we take F, which is 15, and multiply that times 4,096, right? Because this column is worth 4,096. Okay, what is A? What number? 10. So we take 10 times 256. Okay, what's D? B's 13. See, what I do is I always remember A is 10, and then I just go up from that, right? A is 10, B is 11, C is 12, so D is 15. So we take 13 times 16. Okay, and then what's E? 14. 14 times 1. And then we got 4 times the 16. Okay, so now we just gotta multiply these out and then add them all together. 256 times 10, that's an easy one, right? That's 2560. 13 times 16, that's gonna be what, 160 plus 48, so that's 208. This is 14, and this is 46, which is a quarter, right? So the only one here that we might have to do in the calculator is this 4,096. Let's see, 4,000 times 15, that's 60,000, right? And then if this was 100, it'd be 1,500. See, it's like 60 less. It's like what, 1440? So would it be, let's see, what did I say earlier? I said 15 times 4,000, 60,000. And then if this was 100, it'd be 1,500, but since it's 4 less, 4 times this is 60. So if we subtract 60 from 1,500, that would be 1,440, right? I don't know, is this right? Yes, it is. Okay, thank you. So 61,440. So we have to add that to 2560. Oh, this works out nice. Look at this. 560 plus 440. That's 1,000, right? So it'd be 64,000. Did you do that on purpose? Did you know that ahead of time? Okay. You should have said yes. It would have really impressed me. So 64,000. All right, and then this is going to make 64,208, and then 64,222, and then we add a quarter. So we would end up with 64,222.25 to base 10. Okay, if we did all the math right. Everybody agree with this? No errors? Okay, but can you see how it's the same idea? Right, when we went from base 2 to base 10, we did the same sort of thing. It's just each column was, you know, a power of 2 instead of a power of 16. Okay. So does anyone want to see another example, or you get, can you go 16 to base 10? Okay, the next one we're going to do is base 10 to base 16. Great. Base 10 to base 16. All right, so give me a base 10 number, give me something in the tens of thousands, not too crazy, but 14,968. 14,968, is that what you said?
Yeah, 0.2.
Let's not do,
Points.
yeah, let's just do whole numbers here for this one. But well, yeah, let's just do whole numbers. I can talk about that. But yeah, for this particular one, let's just do whole numbers. So 14,968 base. And we want to convert that to base 16. So again, I would write out what the columns are worth for base 16. So 16 to the 0, how many ones? 16 to the 1, how many 16s? 16 squared, how many 256s? 16 to the 3, how many 4,096s? And then 16 to the 4th power, that's the one that's 65,536. Okay, so again, you write out these columns until you get to a number that's more than the number you're trying to convert, right? Because there's no 65,536 and 14,968, of course. So you see, that would just be a 0, so we don't even have to write it. Okay, but now we have to determine how many 4,096s is in 14,968. So how are we going to do that? What would you do? Just divide, right? Yeah, just take the 14,968 and divide by 4,096. And all we care about is we care about what the whole number is. We don't really care what the fraction part is. So what are you going to get? Or you can actually do it on your calculator. It'd probably be 3 something, right? Probably be like 3 points. Did anyone do it on the calculator?
3.65.
Okay, yeah, so it's 3. I mean, the only one we really care about is the whole number, right? It's 0.65, but we don't really care about the 0.65. But we care about the 3. So that means that this is gonna be a 3. So now we take our 14,968 and we subtract from that 3 times 4,096. So that's, let's see, 3 times 4,096, that's gonna be 12,000 plus 300 minus 12. So what, and 12,288? Is that right?
Yeah.
Is that right? It is, okay. And then we subtract this, we'll get 2,000. See, if that was a 6, it would be 700, but what, it'd be 680? I think that's right. That looks right. Okay, so now we have 2,680, and we got to determine, well, how many 256s is in 2,680? Okay, actually, it's probably what? I mean, you could divide, but can you see some character times this is almost that? Almost 10. Yeah, right. In fact, it probably is 10, right? Because if it's 11, I think it would go over, because when this is 10 at 2560, and if we added 256 to 2560, that's more than 2680, right? So I'm pretty sure this is 10, which would be what in hex? Okay. Does everybody agree that this would be 10? If it's 11, it would be more than this, right? All right, so 10 times 256, 2,560. Yeah, you can see here, right? Because when we do the subtraction, 120. So yeah, if we added another 256, it would have been more. All right, now we got to find how many 16s are in 120. See, 5 16s would give us 80. So it's more than 5. Now, how many 16s? It's not 10. 160 is more than 120. Let's see, what's 6 times 16? That's what? 6 times 16 is
96.
96. So if we add another 16, we'll still be under 120, right? So it'd be 7, wouldn't it? 7? That'd be 70 plus 42, 112. Good. So 8, so that's what we have here. So you just, again, keep going till it's 0. Yeah, now, if there was a decimal, it's the same idea. You would have to see like the, whatever this decimal number is, you'd have to see like how many 16ths are, within that decimal part. And if you had some left over, you'd have to see how many 256s, but that can get really gnarly really quickly. That's why I didn't want to do it on this thing. Because yeah, if you pick some like 0.21, you can be going out till, you have 1 over 65,536s, that just gets crazy. All right, but again, what's really important here, the examples themselves aren't really what's important. It's the process, right? Because you do the same process no matter what the number is.
So I must have been down or writing, but I don't really get where you're getting these numbers you're subtracting by the bridge 12,288 came from.
Okay, so where I got this 12,288.
Yeah, and why you're subtracting.
Okay, well, we're starting with this number, right? And again, you always want to write these column values out until you get to a column that's worth more than the number you're trying to convert, because there's no 65,536s in this number, so we didn't even have to write that, but I wrote it just so I'm sure I'm starting with the right value, right? The highest possible value. So we're starting with 4,096. We want to see how many 4,096s are in this number. So that's why we did this division, because that will tell us like the whole number part, right? So now, once I know the whole number part, now I take this whole number 3, multiply it times the 4,096 and subtract it from this. Right, because the rest of this number is gonna depend on the remainder. Alright, so you see, I got the 12,288 by multiplying 3 times 4,096. And then I take that subtract, because now that's what's left over, and that's what the rest of this number is gonna depend on. Right, so when I have this number, I say, okay, now how many 256s are in this number? Right, so it's the same thought process as when we did, the base 10 to base 2, it's just again, the base is different. Yeah, go ahead. Yeah. Did that answer your question?
Yes, that's it.
Okay. And this would be again, base 16, so we put a little subscript 16. Okay? So any questions up to this point? Because the next thing we're gonna do is gonna be a little bit crazy, not real crazy, but a little bit crazy. But is everybody good up to this point? Okay, all right, the next thing we're gonna do, that's a little bit crazy, is we're gonna convert from base 2 to base 16, and we're gonna do it directly. Okay, because one way we could do this is we could go base 2 to base 10, and then base 10 to base 16, right? That would just be combining 2 of the conversions we've already done, right? That would be like a 2-step, okay? But we're gonna do this in one fairly easy step. And this method, for lack of a better name, I call grouping bits. Okay, and you're gonna see that this grouping of bits, it's based on that 2 to the 4th power is 16. All right, so give me a long string of ones and zeros. I want like 17 bits. And let's start with a 1. So give me some bits. What do you want? What do you want next? You want a 0 or what?
0,
You want a 0, then what do you want?
0,
0.
1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1. Where are we at? How many more do we need?
3, 6, 9, 10. Give me 2 more.
0, 1.
Okay. Great. So 17 bits. That's our base 2. Now, like I said, you could take this, go to base 10, and then go from base 10 to base 16, right? You could do it in 2 steps. But we can do it in one fairly easy step based on this relationship of 2 to the 4th equaling 16. Okay, because what I can do with this grouping of bits method, and we would start with what's called the least significant bit. See this bit here that has the minimum value, that's what's referred to as the LSB, which stands for least significant bit. Okay, and then the bit on the other end here that has the biggest value, that's called the most significant. Okay, so what we're going to do here is we're going to start with the least significant bit, and we're going to group these bits in groups of 4. And the reason we're doing groups of 4 is because of this relationship. You want to go from binary to base 16, and there's this power of 4 relationship. So that's where the 4 comes from. So I'm going to group in 4, starting with the least significant bit. So here's a 4-bit group. Here's a 4-bit group. Here's a 4-bit group. Here's a 4-bit group. And then I get to the most significant bit. You can see it's all by itself. But I'll make it a 4-bit group by just adding zeros, imaginary zeros here at the start, right? Because if I add zeros to the left of a binary number, I'm not changing the value at all, right? Just like if I added zeros to the left of a base 10 number, I'm not changing the value. Okay, so I put these here just so I make it 4 bits. Okay, you don't really have to write them. You could imagine it if you want. Okay, so now you write each 4-bit binary group as a single hex character, right? So here, This is the ones column, this is the twos, this is the fours, this is the eights. Right, we're treating this as a 4-bit binary number. So how would you write that as a hex character, 1101? What's 1101 in base 10? 13, and how do we write 13 in hex? D, right? So that would be a D. Okay, and then I do the same thing for the other 4-bit groups. I treat each 4-bit group like a 4-bit binary number where this is the ones, this is the twos, this is the fours, this is the eights. So how would I write 0101 as a hex character? 5. Okay, what would I do here? 4. 3. 1. So 001, 0011, 01, 0001, 011101 in binary is equal to 1345D in hex. And wasn't that a lot simpler than going from base 2 to base 10 and then base 10 to base 16? Okay, and if you don't believe me, if you don't believe that this works, well, take this base 2 number, convert it to base 10, take this base 16 number, convert it to base 10, and you'll see you'll get the same number. Guaranteed. Right? So I recommend that, you do that at some point just to convince yourself that this actually does work. Okay, and it works the other direction too. Like we just went from base 2 to base 16, but you can use the same grouping of the bits in reverse to go from base 16 to base 2. And give me a base 16 number, for characters, where again, some are letters. They don't have to all be letters, but don't have a 0 either. Oh, you could have a 0, I suppose. Yeah, actually, let's make one of them 0. So give me 4 hex characters, like 2 letters, a 0, and some non-letter 1. Anybody wants to give me a hex number? Again, the questions get harder as the quarter goes on. How about Ethan? You want to give me a number back there?
And base 2.
No, base 16.
Oh, base 16.
One character has to be a 0. At least one has to be a letter, and then give me a non-letter.
2B, 3A.
Okay, 2B. Let's make it 0 then, because I wanted a 0. Okay, thank you. All right, so we can convert this base 16 number to base 2 by writing each hex character as a 4-bit binary. So we're just doing what we did here in reverse. So how would you write F as a 4-bit binary? What's F in binary? What's F in binary?
1111.
Yeah, it's 15 and base 10, which is all ones, 4 1s, yes, and binary. So 1 1 1 1. And I'd write 0 as what? Would I just put 0? No, 4 0. Because it's got to be 4-bit binary. That's why I wanted the 0 there, because that's a common error people make. Common error, they go, oh, 0, I'll just put 1 0, but they all have to be 4-bit binary. So it's got to be 4 0. Okay, how about B? What are you going to write for B? Because what's B in base 10?
11.
11. So what's 11 in binary? No. Wait, what was it again? Oh, there we go. I didn't hear the 1, I think, when you first said. But yeah, 1 0 1 1. Okay, and then how we would write the 2?
1 2.
Yeah, 0 0 1 0. Now, because these zeros are at the beginning, you could get away with not writing them, right? Because it doesn't change anything. All right, but technically it would be 0 0 1 0. Okay, so you see 2B 0F in hex is 1 0 1 0 1 1 0 0 0 0 1 1 1 1 in binary. Okay, and again, it's all based on the reason we're grouping in 4s is because 2 to the 4 equals 16. So what if I wanted to go from base 2 to octal? What if I wanted to go from base 2 to base 8 grouping bits? What would be different? Right, why would we group in 3s instead of 4s? Right, because 2 to the 3 is 8, exactly. So you see, if we started with this binary number here, and we wanted to go to octal directly by grouping bits, we'd start with the least significant bits and do groups of 3. And then we would write each 3-bit group as an octal character, right? So this would be 5, this would be 3, and so on. Okay? Does that make sense? And you see the reason why hexadecimal is so useful and very popular in the digital world is because often in practical digital circuits like a microprocessor, you have data that's many, many bits. Like in your CP 233 class, the follow-on class for this one, you're going to build a microprocessor. And that microprocessor is 32 bits. That means the data is 32 bits. So you're going to have data that's, 0, 1, 1, 0, 0, 1, 1, like 32 zeros and ones. Well, how many hex characters would it take to represent 32 bits? Like if I had a 32-bit number up here and I use this grouping of the bits to go from that binary to hex, how many hex characters would I end up with if I start with 32 bits? 32 ones and zeros, 8, right? Because you got 32 ones and zeros, you group them in 4s, right? It could be 8 groups of 4, and each group of 4 gives you a hex character, right? So you see, hexadecimal is sort of like shorthand in the digital world, right? Because I can say a long string of 1s and 0s in a lot less characters, right? I can say 32 bits in 4 hex characters. Okay, so that's what makes hexadecimal, popular. Like when you take CP 233, and also in this class we use it, but in particular within CP 233, you're going to be dealing with data that's in hex instead of binary. Now it represents binary, but it's a shorthand for all those bits. Okay, so you're going to be doing conversions like this. We do it a lot in any sort of digital class. Okay. Okay, so do you have any questions about? Oh, one last thing before you start the activity, and that's, once you understand, what we've talked about here about the bases and how to convert, you should be able to convert any base to base 10. Like, for example, based on what we talked about here, if you had, say, a base 5 number, say you had this in base 5. First of all, is this a valid base 5 number? And what do you think I mean by valid? In hexadecimal, would this be a valid hexadecimal number? Why is it not valid?
G is.
Right, because we don't have G in base 16, right? We only go up to F because there's 16 characters. So is this a valid base 5 number? Yeah, right, because in base 5 you have 5 characters, 0 through 4. But if you had this, is that a valid base 5 number? No, because 5 is not a character in base 5. Okay, you see that's a common error because, again, people forget that 0 is a character. Sometimes they forget that. So yeah, we had that. That's a valid number. And now, if you wanted to go to base 10, it's the same idea as what we've been doing with the other bases. This is 5 to the. This is 5 to the 0. How many 1s? This is 5 to 1. How many 5s? This is 5 squared. How many 25s? This is 5 cubed. How many 125s? This is how many 1/5, right? Because that's the 5 to the minus 1. And then you would just do like we've done before, 4 times 125. You'd have to add that to 3 times 25. This is going to be 0. And then you'd have 2 times 1. And then you'd have 1 times 1/5, right? So let's see, this is going to be 500. 75, 0, 2, and a fifth. Add those together, what, you get 577.2 in base 10. Okay, so you see how it's the same idea as what we've been talking about earlier? Again, base 5 doesn't come up in digital, okay? I'm just showing this example just to show you now that you can do it for these bases that are popular in digital, you can do it for any base. Okay. All right, so that's all I wanted to lecture on today. So the next thing is the activity. If you want to take a break before you start the activity, that's fine. Again, everyone should have a sheet like this. Okay, so everybody does their own work, and then you just pass in one for your table. And I'm providing the answers. Okay, this sheet has the answers, and I'll put it right here at the end of the table. You can come take a picture of it. Okay, don't take it, just take a picture of it so other people can also take a picture. And like I mentioned on Canvas, the activities aren't graded on accuracy because I give you the answers. I just grade them on complete. I just look to see that work has been shown. You do have to show your work. Just don't write the answers because I'm giving you the answers. I want to see that you can do the work. Okay. And if you have questions, you can help each other. Again, I encourage collaboration. And also I'm here to answer any questions you have.